Hello everyone, I am Bo-hyun Lee from Sungkyunkwan University, and thank you for clicking this video. In this video, I am going to present a paper titled LRUC Parallelizing Database IOs for Flash SSDs. These are the indexes. And so first, let me summarize this paper by briefly explaining the motivation and the contribution of this paper. While running various experiments, our team realized that the existing database systems tend to serialize I/O requests, even though they are fully able to process multiple I/Os in parallel using flash SSDs with high internal parallelism. And we found out that there are two main reasons behind this: the read stall problem and the mutex conflict in the LRU list. Therefore, to solve these I/O serializations, this paper proposes a novel database I/O architecture called LRUC. The whole I/O-related buffer management works based on the LRUC pointer, which holds the least recently used clean page. Also, we separated the global LRU mutex into two mutexes, LRUD and LRUM, which protect the two different regions of the LRU list. By prototyping LRUC on MySQL InnoDB engine and running various experiments, the results confirm that LRUC outperforms vanilla MySQL by 3 to 5 folds, and the state-of-the-art WAL solution by around 50%. Next, I will point out some important background information of flash SSDs and database buffer manager that connects to the motivation of this paper. First, flash SSDs are well known for its read-write asymmetry. In other words, the read speed of the flash SSDs are 5 to 10 times faster than the speed of write. Second, flash SSDs support internal parallelism at various levels compared to the hard disk. Therefore, in order to fully leverage the bandwidth of flash SSDs, the host system must allow different threads to issue their I/O request in parallel. Next, I will review the I/O architecture in the database buffer, assuming it uses a LRU-based buffer replacement policy. Generally, the foreground user thread reads a missing page from the disk by going through these following steps. First, it searches for a clean buffer frame in the free list. If there isn't no available free buffer frame, next, it scans from the LRU tail looking for a clean victim. However, if there is no clean page within the predetermined scan depths, it has no choice but to flush a single dirty page from at the end of the LRU tail. So in the worst scenario, the foreground user thread must wait for the disk write to be performed first in order to read a missing page from the disk. Meanwhile, the background flusher periodically flushes a certain number of dirty pages at the end of the LRU list to produce a free buffer for the foreground thread. Likewise, the foreground thread and the background flusher competes for the same global LRU mutex, even if they target totally different pages in the LRU list. Next, I will explain the reason why these characteristics of flash SSDs and database buffer manager causes I/O serializations. As I explained before, the read request is stalled by the write request, and the dirty page is selected as a victim for replacement. This phenomenon is called read stall, and in this paper we accuse this read stall as one source of I/O serialization. As you can clearly see in this figure, the write request and the read request is issued one by one. So we define this type of I/O serialization as read-write serialization. Some of you might probably think that this rarely occurs. However, when using flash SSDs as a storage device, we witness that 20 to 30% of page read request secures a free buffer frame by going through step 3-1 in this figure, instead of getting a free buffer frame in step 1 or step 2. So as a result, restall worsens the transaction throughput severely and the tail latency as well, and CPU is less utilized since CPU idly waits for the synchronous writes to be finished. This is because of the read-write asymmetry of flash SSDs. Due to the speed gap between the read and the write, the free buffer consumption speed by the foreground readers is way faster than the free buffer production speed of the background flushers. Therefore, restall is a general problem, especially in the case of workloads under I/O-bound situations with numerous concurrent threads. Second, read-write serialization occurs as the foreground reading process and the background writer compete for the same LRU mutex. Even if the background writer flushes 30 pages asynchronously, it must wait for the mutex to be released when the foreground reader is holding it. And the final type of I/O serialization is called read-read serialization, and this happens also due to the mutex contention of the LRU list. In the previous slide, the figure shows the procedure of the single foreground process issuing the read request. As the foreground process goes through those following steps, other foreground processes are idly waiting for the mutex to be released. So please keep in mind that the longer time the foreground reading process takes during those steps, especially when they are looking for a clean page, the longer time the other foreground readers have to wait in order to acquire the global LRU mutex. So to summarize, the current database system serializes I/O requests due to restall and mutex conflict, and in this paper, we define 3 types of I/O serializations accordingly. The first is read-write serialization by restall. And this is a type of serialization that occurs within the single foreground thread upon page miss. And the second one is read-write serialization between the foreground reader and the background flusher. And the final one is read-read serialization between the foreground readers. And the last 2 serialization both occur as they all require LRU mutex acquisition before doing any operation that manipulates the LRU list. Now, let me explain how LRUC resolves these 3 types of I/O serializations. LRUC stands for least recently used clean page, and the LRUC pointer holds the least recently used clean page in the LRU list. This pointer is used for both foreground reader and the background flusher. We also extended LRUC with 2 further optimization. The one is dynamic batch write, and the other one is the parallel LRU list manipulation. So let's first see how LRUC works upon page miss. Like before, the foreground thread first looks for a free buffer frame in the free list. If there isn't any, then LRUC scans for a clean page after the LRUC pointer. This is very beneficial because it only has to scan only 1 or 2 pages from the pointer, whereas vanilla MySQL had to scan all the way from the LRU tail. When it finds the next LRUC page, the pointer is updated, and that according buffer frame hashing the clean page is used for replacement. This way, we can read a missing page from the disk without encountering any restall, and thus without issuing any additional disk writes. So far, what we did was to speed up the read request by resolving restall-induced read-write serialization. However, the remaining problem is that the free buffer frames are more quickly consumed than before, but the speed of the background writers remains the same. Therefore, in order to speed up the background writer's free buffer generation speed, we came up with an optimization called the dynamic batch write. In this optimization, background flusher writes all the 30 pages between the LRUC pointer and the LRU tail, since we know that all the pages after the pointer is 30. And it flushes all those pages in a single batch. Second optimization is parallel LRU list manipulation, and the purpose of this optimization is to remove the read-write serialization between the foreground reading process and the background writer. So this is sort of the final LRUC overview, and the interesting thing about the LRUC pointer is that it eventually dissects the LRU list into 2 regions, mixed region and the dirty region. Mixed region contains both clean and dirty pages that are mainly accessed by the foreground users, whereas the dirty region contains only cold and dirty pages that are mainly accessed by the background writer. So by exploiting this fact, we divided the global LRU list mutex into two mutexes to enable simultaneous access of the foreground and the background processes to the LRU list. So as a result, LRUD protects the dirty region, and the LRUM mutex protects the mixed region. Therefore, the foreground reader and the background writer can issue read and write requests at the same time by acquiring two different mutexes. So with these modifications, LRUC brings three immediate benefits by resolving the three I/O serialization explained earlier. First, LRUC resolves restall-induced read-write serialization by immediately serving LRUC page for replacement. Second, it also mitigates the read-write serialization between the foreground processes and the background flusher by splitting the mutex of the LRU list. Finally, it also alleviates the read-read serialization by shortening the scanning process when looking for a clean page during the page miss by introducing an LRUC pointer. A single drawback of LRUC is that it reduces the hit ratio slightly. This is because LRUC uses a warmer but clean page as a victim for replacement. However, reducing I/O serialization far offsets the reduced hit ratio according to the experiment result. And please refer to the paper to check the exact hit ratio comparison result. So from now on, the rest of the slides show the evaluation results. We prototyped LRUC on MySQL InnoDB engine and ran various experiments using workloads, devices, number of concurrent threads, read-write ratio, and such to prove the effectiveness of the LRUC. So this figure shows how TPS varies when using different versions of LRUC. So it clearly shows that two optimizations are indeed effective. And the effectiveness of LRUC is valid not only on TPCC workloads, but also on Linkbench as well. And in order to investigate the effect of read-write ratio on LRUC, we also varied the read-write ratio of the TPCC benchmark and confirmed that the related performance gain reduces as the write ratio increases. And to verify the effect of the number of concurrent threads on LRUC, we also ran the TPCC benchmark while varying the number of concurrent threads. As you can see in this figure, when we increase the number of threads from 8 to 60, 32, and so on, LRUC improves the scalability and the concurrency of the database system. And we also compared LRUC with vanilla MySQL on a simulator called Cosmos OpenSSD to see how TPS changes as channel level increases. And as expected, LRUC works better with more internal parallelism. Lastly, we also did experiments on 3 other commercial SSDs, and also cloud storages and hard disk as well, and checked that LRUC works on any SSDs, including GCP and Azure. However, when using hard disk, LRUC is not effective since there is no room for improvement on hard disk with no parallelism. In summary, LRUC improves the transaction throughput and resource utilization by parallelizing I/O requests, by addressing I/O serialization caused by restall and mutex conflict. And we would like to emphasize that LRUC not only brings prominent performance improvement, but it has a simple but effective design. Also, we would like to extend LRUC on other systems, such as operating systems in the future, since it is applicable to all the systems with an LRU-based replacement policy. So this is the end of our presentation. And if you have any questions about the paper, please feel free to email me on this slide. Thank you for watching this video and have a nice day.